Section 6.7 is focusing on area of triangles and quadrilaterals. So we're going to still see some triangles that we've seen before. We've already talked about the areas of those, but we're going to be also doing some combinations of shapes too. So we're going to see some quadrilaterals as well. And of course, so 2- and 3-sided figures for the most part.
Yeah.
Now, the first postulate we're looking at, and this is a postulate, so it's just accepted to be true, it deals with area congruence. And it says that if 2 polygons are congruent, then they're going to have the same area. And that's something that I think some of us, it seems like a no-brainer, and hopefully it's a postulate. It should seem like a no-brainer. But if 2 figures are congruent, meaning that they have what?
All their corresponding sides and angles are all congruent.
Right. So then wouldn't it make sense that because they're basically the same
shape and
size, they should have the same area?
Yeah, that's kind of
sense.
No-brainer.
And the second one is talking about area addition. And this says that if the area of a region, so if I talk about this whole larger region, when I'm looking at that whole area, it's really the sum of the areas of the non-overlapping parts. So I could look at the area of just this rectangle, and I could look at the area of this triangle, and if I added those 2 areas together, that should make the area of the entire figure.
Makes sense.
Okay? So again, these are postulates. They're kind of no-brainers, but just want to make sure that you guys are aware of these 2 things.
And this one right here, what's nice about the area addition is if you don't really know what kind of shape it is, obviously this region isn't really made up of just one shape. So you might, and you can often break it into pieces. Even if you know it's a certain like quadrilateral, but it makes sense to break it up in pieces that make up it. So we're going to see some of those examples involving this. This is one that you might use, and you may have used it already. All right, now this next slide is going to focus on 4 of the, I think 7 different area formulas we're going to do. Now, most of these on this slide you've seen before. For example, area of a triangle, we've already talked about it.
We have, yes.
Area of a square, we've already talked about it. Area of a rectangle, we've already talked about it. Area of parallelogram is somewhat new, but you may have had some exposure to it before.
Right.
Okay, so this slide is just more real quick recap. All right, so what is the area of a triangle?
Area of a triangle is 1/2 the base times the height.
And remember, 1/2, don't forget that. Okay,
Yeah,
a
that's
lot of
the
people
part that
forget that. Now, taking a half of something is the same thing as,
Dividing it by 2. So I could say base times height divided by 2.
so that's another way you could write that formula. Now, I want to stress something because the base, often people think, okay, the base has to be the bottom side. Okay, the base just has to be what?
It has to be the piece that's perpendicular to that, or that's got that height that's coming into it.
Okay, so but what is a base?
Oh, it is a side.
It has to be a side.
It is a side.
So a base is just a side of some sort. Okay, it could be any of the sides. It just depends. It really depends on the other piece, the height. Now the height has to be perpendicular to the base. Ms. Hope-Gravy kind of mentioned that, right? So in this particular triangle, let's say acute triangle, if this is the base, the height would be the piece that would be perpendicular to it. Now, another name for the height we learned in chapter 5 is
the altitude.
Altitude. So we learned that there are 3 altitudes technically in a triangle. So there's going to be 3 different heights. It just depends on which one it is. It all really depends on
what they give you.
What they're giving you.
They're going to give you a height. You just have to know then what base corresponds with that height.
Now, in a right triangle, this one's kind of unique. If I told you, let's say this is the base, then the height would be
that bottom side.
Yeah. It's the other leg of that right triangle.
To it.
Yeah. All right. Now, in an obtuse triangle, let's say I drew a height that's perpendicular. Notice it could be outside. We've talked about that. So the base would be this side right here. Now, it's only this a side. It doesn't extend out. So the base is just a side. So keep that in mind. All right. Okay. Area of a square.
All right, well, we could call the side lengths just S if we want to, just to represent, because we know they're all the same.
Okay.
So we know, like, in a rectangle, we're probably thinking base times height. You don't even need...
Let me jump down there.
Yeah, sounds good.
I'll just write that. So area of a rectangle is base times height.
So, but here, you don't really need to say base times height because the base and the height are all the same side length. So if I called all the side lengths there S, I could just say S squared.
Okay.
Now, you could still say base times height. I have a lot of kids that for squares will say base times height.
Yeah, you
and
can.
That's fine. It's still, squares are rectangles.
Well, and that's exactly. Remember back last night when you were watching this video, remember when we did that flow chart, any characteristic of a square had characteristics of a rectangle because it is a rectangle.
Exactly.
I do like just doing side squared because then you're just squaring a number. Okay. Yeah. Now, a rectangle, base times height. Now, same rules apply. A base is a side. The height has to be perpendicular to it. So in a rectangle, what's kind of unique, or not unique to a rectangle as well as a square, is that the height is also a side. Okay, so keep that in mind. In a triangle, it wasn't. But in this case, why is the height could be a side? Well, because every side is perpendicular, or consecutive sides are perpendicular to each other. Right? So just remember that. You'll also hear length times width sometimes. Our book likes to use base times height, so just be aware of that. Okay, now in a parallelogram, okay, now some of you might have an idea already. Now, a parallelogram obviously is not necessarily always going to be a rectangle, okay, but rectangles are obviously parallelograms, so keep that in mind. Now, something that's kind of cool, if I take this little triangle, kind of move it over here, did I really change kind of the area of this figure?
No.
I changed the shape because now what kind of shape do you see?
Now it's a rectangle.
It's a rectangle. And what do we know about the area formula for a rectangle?
It's base times height.
Base times height. So technically, in a parallelogram, the formula for it is
base times height.
Exactly. Now, this is one where you have to be careful. What would be the height?
The height has to be perpendicular to the base.
And the base has to always be a side length, okay?
Right.
So keep this in mind right here. This is kind of important for any of these things when you have base and height. So the height has to be perpendicular to the base. So let's say this is the height. So the base would be this entire side. Not part of the side, the whole entire thing, all right? This could be a side, all right? Now, the height wouldn't be another side. You would have to make sure you have a segment that's perpendicular to it. So it just always, again, depends on what you're given. Now, one thing to notice before we move on to the last three is notice that the formula for area of a parallelogram is base times height. Rectangle?
Base times
base
height.
Times height. Why?
Because they're, well, really all, if I didn't know that the area of a parallelogram is base times height, then all rectangles also follow that criteria.
Exactly.
Because they're also parallelograms.
Kind of going back to yesterday.
And squares, we could use base times height also.
This could also, if you wanted to write base times height. Why? Because it has characteristics of a parallelogram.
Okay.
So keep that in mind for the ideas, okay?
Okay.
So with a rhombus, it is a parallelogram, right?
Right. So I could use...
You could say
base
area
times.
is base times height, okay? This is helpful if you know one of the side lengths and you have a segment perpendicular to it. Now, rhombuses are kind of unique, okay?
Okay.
There is another formula for it, and it involves the diagonals. So let me draw on those diagonals.
So there's two formulas for the same shape? Oh, my goodness.
I know. But if you notice, there was for a square, there was two different formulas.
That's true.
And it all really depends on kind of the shape. Squares are very specific, very unique, so there's a lot of characteristics it has. Rhombus are kind of unique as well. All right, so we could use this one. And this one doesn't always work nicely because maybe I'm giving you the diagonals. Now, what's unique about rhombuses is that there's something special about the diagonals, okay? That's only unique to a rhombus, not like necessarily a rectangle, okay?
Okay, well, I remember the diagonals were perpendicular.
Now, were the diagonals congruent in a rhombus?
No, they weren't.
No, so we're going to call our diagonals, we're going to label them D1 and D2, and it's kind of hard to, label that in the picture necessarily. So one of the two different diagonals.
Okay.
So to find the area, right, it is 1/2 D1 times D2.
Okay, so that's another formula we could use.
Specific to a rhombus, all right? Now, will you always use that formula? Not necessarily, but if you're given the diagonals, well, that's pretty easy formula to remember, all right? Now, going back real quick, with a rhombus, we know this is the formula. Is there anything on this last slide that has the same characteristics as a rhombus?
Well, I know that parallelograms have some similar...
But is it the same?
Oh, not the exact same characteristics.
Okay.
I know that squares had some, but not all. Well, no, squares do have all.
Yeah.
I'm trying to think about that. Squares do have all.
Yeah. So I could technically
all rhombuses are
I
squares.
could technically use this formula for a square as well.
Okay, because all squares are rhombuses.
Now,
right.
again, you may not need it, all right? But just keep your options open. Remember back to yesterday, that flow chart. Squares had characteristics of a rhombus, okay? Because a square is a rhombus, technically.
That makes sense.
So,
now, that formula, where did that come from?
good. What do you think?
Well, I'm thinking because the diagonals are perpendicular, it has something to do with maybe those right triangles. Is that where that's coming from?
You're exactly right.
Okay.
You're exactly right. And here's the deal. Isn't it also in a square, the diagonals are also perpendicular?
They are.
Okay.
So really what you could do, thinking about that area addition postulate that we talked about, you could find the area of one of those little right triangles, and they're all going to be congruent triangles. So you really could take 4 times that area of the one triangle.
Yeah.
I just want you guys to realize where all this stuff's coming from.
Exactly. Now, speaking of that idea, okay, I want you to think about with a kite. And I'm going to give you a little hint. It does involve, the formula involves diagonals. And there's a reason why. If I draw them in, what do we know about a kite and its diagonals?
Well, we know the diagonals are also perpendicular.
So kind of that similar idea, the fact that these are perpendicular. So what Ms. Hograve is kind of mentioning is that you could find these individual triangles here, all right? You could find the area of each of those and add them together. If you don't remember that idea, that's totally fine. But because the diagonals are perpendicular in a kite as well as in a rhombus, as well as in a square, you can use the same formula. Okay.
So really knowing those properties is going to be helpful to know what formulas we can use.
Exactly.
So when we see that perpendicular diagonal idea, we know that we can use the formula 1/2 d 1 d 2.
Exactly. All right. Now the trapezoid, last one. The trapezoid's kind of the unique one.
Oh, yeah.
All right. And this is one I like to kind of show you kind of a little visual to kind of see where this comes from. Notice, okay, what we know about a trapezoid. Obviously, it's not the same as a parallelogram because it doesn't have 2 sets of opposite sides parallel. But it does have 1 set, okay? And in that 1 set, okay, those are the bases. Now, are the bases going to be congruent to each other in a trapezoid?
No, not at all.
No, they're never going to be. If they were, then that makes it end up being a parallelogram. So I'm going to call this B1 and B2.
Okay.
All right. Now, notice I drew in a height. So it probably has something to do with that. All right. So the things I have labeled in the picture, it involves with the area. Now, if I take a complete copy of that trapezoid, okay, and I'm going to kind of flip it around, move it right here.
Oh, it's a parallelogram.
Notice the 2 exactly the same trapezoid put together makes a parallelogram, right?
Right.
Okay, so if I know that, but I only want to find the area of one of them.
So I need to do half of it?
Now, here's the deal. This whole base, we know to find the area of a parallelogram, it's the base times height, right?
Right.
But this whole base is actually made up of
B2
and B1. So if I add those together, that's the whole base times the height. Okay, now if I do that, so the B1 plus B2, that times the height, but I only want one of them, and you said...
So I've got to do half of it.
Half of it, so I could just cut it and multiply by half or divide by 2. All right, well, that 2 kind of looks weird. You could write it like that. Now, what about could I put the height like right here? Could I do 1/2 height?
Sure, it's multiplication.
Yeah.
Order doesn't matter.
So it just doesn't really matter there, okay?
Yeah.
So that's kind of showing you where that came from in a sense.
And one thing that I like to say to kind of remind us, where that B1 plus B2, that sum of the bases. Remember when we did the mid-segment of a trapezoid? That's really what we're doing is we're averaging the bases.
Exactly.
So if you average the bases times the height, but only take half of the average of the bases times
So really, in a sense, this part right here, I'm circling that represents the mid-segment. So you could think of it also, to find the area of a trapezoid, it's really taking the mid-segment
times
the height. So not very often will they give you the mid-segment. Most of the time they'll give you the 2 bases.
Right.
So it's averaging the bases and multiplying by the height. Okay, so just remember that. All right, we're going to apply some of these formulas finally.
Yes, there's a lot here. And as we go through these, is it actually ask yourself first, what shape do I have? So what shape do we have in this one?
Well, they tell it's a triangle.
Okay.
But I also can tell in the picture it's a triangle.
Absolutely. And we know the formula for the area of a triangle
is 1/2 base times height. And I love that Miss Hookerby had me do that. What kind of shape is it? What's the formula?
Right.
Those are the 2 questions you want to ask right away.
And we're really going to want to see on your paper that you know exactly what you're using. So it's helpful if you just start by saying, okay, what shape do I have? What's the formula? Write that formula down, because then it's just a matter of substituting numbers in. Okay? So looking here, the important thing that we said we kind of need to look for first is the height. Do you see a piece that is showing an altitude?
Yes.
Right.
That's 4.
4
so
is
4
our
is
height.
the height.
And we know that because it's perpendicular to the base. Now
side.
notice that it's kind of off to the side a little bit, but that's okay. If I continued that line where the base is on, it would be perpendicular to that line.
Okay.
Okay, so there's my height. What would the base then be?
So it'd be 1/2 the base, which would be the side of 6, and times the height of 4.
Right. So we know we want to take 1/2 of our base times our height. The height, again, has to be the piece that is perpendicular to that base.
And one thing to notice, there is another side labeled in the picture, which is the 5, but there's nothing labeled perpendicular to it.
So we're just not going to use it. All right,
Okay.
and when we multiply this,
so that ends up being 12.
yeah, and guys, it doesn't matter if you do half of the 6 first, if you do the 6 times 4 first. Order doesn't matter in multiple.
You could do 1/2 times 4. It
And
doesn't
if
matter.
there's units, we would want you to go ahead and label. Since there's no units here, just 12 will be fine with us.
Okay.
If you want to say units squared, you can, but we're not going to be super picky.
You're not squaring the 12, so don't put 12 squared.
Right.
I've seen people do that.
I
12
have too.
squared is 144, not 12.
the same.
All right. So what kind of figure do we have?
We have let's see, we know it is a parallelogram.
Okay, it says it. We also can kind of, here's the deal. They don't really, in the
Can't really
picture,
see
you
it in
can't
the
see
picture.
And that's why it says, find the area of this parallelogram. So reading those directions probably important there. Okay, so how do we find the area of a parallelogram?
It's going to be just the base times the height.
Okay, so looking at that picture.
Now, I see a couple heights marked in this picture.
So let's pick one. All right, and then kind of go off of that, and then maybe we have another approach, and we can talk about that.
Okay, well, if I use the 12, I see that that's perpendicular.
So if this is the height,
then its base would have to be the other 12 down there.
this would be the base. Okay, so it would just be 12 times 12,
You got it.
which is
144.
144. Again, there's no units provided, so you don't have to label. Now, another option is what if
I use my 9 as
the
my
9,
height?
because this is necessary. This is actually perpendicular, and it's perpendicular to what side?
The 16.
So this would be the base. So if I hopefully would get the same thing.
Yes, and you
So
do.
it'd be the 16 times the 9, which would also get you 144. So a couple options.
Yeah. All right, for this next one, find a base length in a trapezoid with an area of 30 and a height of 12, and the other base length is 2. Now, what does this not have that the previous ones did have?
Well, one thing I noticed that it does tell us is that they're telling you the area. So it's nowhere is it saying find the area.
Right.
They're giving you the area, which basically means there's probably something missing involving like kind of some kind of side or maybe a height of some sort.
Okay.
So I'm looking, the fact that they're saying find a base length, that's the first thing that I read, find the
Right.
base length. That means I don't know one of the base lengths, basically. So that's what I'm trying to figure out.
Okay.
But I'm dealing with a trapezoid, so I'm still going to think about that formula. So area equals, let's do B1 plus B2 in that quantity
Oh, okay. Sorry, I'm trying to figure out what you're doing. Okay.
times the height
Times the height.
all over 2.
Okay. That's where I thought you might be going.
Yeah. Instead of the half. Because guys, you can use the half times that. But I think there's a lot of you that struggle with fractions, so this gives you another option.
Yeah. And guys, one thing I wanted to mention too, this doesn't have a picture with it. If it helps, draw the picture. All right, so you know it's a trapezoid. You have that one of the base lengths is 2. I'm going to assume maybe that's the shorter one. I don't know. And we know the height is 12. And I'm finding the other base length.
Okay.
And I know that the whole area is 30. So if it helps, draw the picture.
Okay.
Okay, if they don't provide one, that's always okay. All right, now, what are the pieces that we know?
We know that area is 30, so I'm going to put 30 in for the A. And then we don't know one of the bases. And does it matter which one?
Nope.
No, so let's just say we don't know B1. So B2 is 2, because that's the other base. Put that in parentheses times the height, which is 12, all over 2.
Great.
Okay, now, really, guys, all you're doing is solving an algebraic equation. Now, how you go about it really doesn't matter, okay? One thing I can see is I could go ahead and divide 2 into the 12, all right?
Okay.
I could do that, all right? Now, if that height was not divided evenly by, if it wasn't divisible by 2, let's say the height was 13, I probably wouldn't do that, all right? So it just kind of depends on how you go about it. So 30 times equals the B1 plus the 2 times the 6. And then I would go ahead, I could distribute.
So we're going to get 30 is equal to 6B1
plus 12. And then subtract 12, so I get 18. Yep. Sorry, I don't know why I said 8.
It's okay.
I'm thinking,
well, 6B1.
so the base 1 would be 3.
All right.
Now, another way you could have done it, instead of distributing through, you could have divided both sides by 6. Again, lots of options. Now, could I check, because I'm solving an equation technically. So could I check it?
I think that'd be a great idea. So what we're saying is that this 30 should equal our 3 plus 2 times 12 divided by 2. Well, what do you know about 3 plus 2?
5.
And 5 times our 12.
60.
And 60 divided by 2?
30.
Gets us
It
back
works
to our
out.
30.
All right, now, we've dealt with some stuff with coordinate planes quite a bit, so we should be comfortable with some of these things. Now, this one we're not deciding what kind of figure it is,
Hallelujah.
okay? But we are trying to figure out the area, all right? So we're finding the area of a rhombus, okay? So the key here is we already know it's a rhombus. So when we find the area of a rhombus, we need to know
What formula we're
what
using.
formula to use. Now,
And there's a couple that we said we could use
what
for
are
a
the
rhombus.
ones that we could use?
We could do 1/2 of the D1 times D2, but I could also do the base times height.
Now, how do we know which one we're going to use?
Well, I'll tell you that if it's me, I'm looking at this and I could find those two diagonals just by using the distance formula.
Okay, well, if we kind of have the information provided, yeah, we could do that.
Because I've got some coordinates
Couldn't
there.
you find the distance between for the base?
Well, I could find a base, but the height might be a little. Well, no, I could.
You could.
I could maybe
possibly.
do it, but it would just be a little trickier because we need to make sure it's perpendicular, and I don't know exactly where. Without drawing a picture.
I think here's the key. Here's the key. It really what you need to keep in mind is it depends on which one would be the easier to do.
Okay.
Okay. Which one provides the information where we could do it the quickest.
Okay.
All right. So I think also what Ms. Hokery said that's really important is without a picture, we really don't know. Okay. So the fact that they give you the coordinates of your vertices probably means we're going to graph it, right? So let's
And
do
really, if we use that 1/2 D1 D2,
Yeah.
you really don't need to graph
that's
it at
true.
all.
But if you want to see kind of what would be the best approach, all right,
It might be easier to.
it might be easier to make that decision, okay? Because, finding the base and the height maybe, who knows, all right? So let's go ahead and graph it just to get a visual of what we're dealing with. So this is my E. This is my F. This is my G. And this is my H. Okay, so if I connect those vertices, now they're telling you it's a
It's a rhombus. We don't even have to guess.
We're not proving anything, and hopefully you see it there. Okay, now.
Oh yeah, I definitely want to use those diagonals.
Yeah, and this gives you kind of a good approach of kind of seeing what you're dealing with here. And notice if I do draw in those diagonals here, let me pick a color you can see, a little Christmassy. Notice how convenient those two diagonals
they're
would
horizontal.
be.
So could I even count them?
You could.
Okay.
Okay, because you're not really showing anything. You don't have to show me that. And that's kind of, the good reason to kind of draw it. Now, drawing a sketch might take some time, all right? So if you don't want to do that and you want to go ahead and just use the distance formula, finding the distance between the two diagonals, that works as well, all right? So what are the two diagonals?
Okay, let's see here. I'm looking at GE first.
Okay, so that's one diagonal.
And that should be 8.
All right. And what she's doing is just kind of counting from, the distance here. Or you can look and see, okay, this is -3, this is 5.
Ooh, ruler postulate. Look at that.
So you could do 5 minus a -3, which is also 8.
Okay.
All right.
And then for HF or FH, that diagonal is 14.
Again, you could use that ruler postulate. This is 9. This is -5. So 9 minus a -5 gets you that 14. All right. But we still haven't answered the question, right?
Nope.
So
the area would be 1/2 of 8 times 14.
And the reason why we can do the half times the 8 times 14 is that these are the diagonals. All right. So this would be 56.
Perfect. Okay. So then this next one, it says find the area of the figure shown. And what kind of a figure do you see here? What kind of a figure is this?
This is a kite.
It's a kite. Okay. And how do you know that? Because they didn't tell us what the figure was.
Well, because I'm looking at the picture and I see 2 sets of consecutive congruent sides, but opposite sides are not congruent.
Right. Okay, so we know we've got a kite. And what's the formula that we know to help us to find the area of a kite?
Well, the formula is 1/2 D1 times D2. And the other thing you could, again, we talked about, you could find individual pieces. I see inside that figure, that kite, there are basically 4 different rectangles, 4 different triangles, so you could find the area of each of those.
Right.
Now, you labeled something in there. How can we know that?
Well, yeah, and I probably shouldn't have done that until we talk about it. But we know that anytime we're using this formula, that's another key to us, too, that you're going to have perpendicular diagonals.
And that's something we learned a few days ago.
Yes.
Perfect. Okay.
Okay. And as we're looking at this right now, do we have enough information to talk about just 1/2 D1, D2? Do we have both of those diagonals?
No, technically we only have one because there's that one that's labeled the 16 and 3. So one of the diagonals is actually 19. So we have one of them, but we don't have the other one. But there is something they're giving us. And there's, again, think about why they're giving you this. They're giving you a side length.
Uh-huh.
And I noticed that side, along with part of that other diagonal, that 3, forms a right triangle with another part of the other diagonal. So I probably can use the Pythagorean theorem.
I think that's a great thought. All right, so we're going to write this as?
So 3 squared plus, let's say, b squared is equal to 5 squared. So, and b squared ends up being, in the end,
25. Gosh. So b squared will be a 16, so b is 4.
So label that. Okay, and I remember from kites that one of the diagonals ended up being bisected.
Mm-hmm.
Okay, those end up being both 4.
So that whole diagonal would be?
It is 8.
Great.
So we're going to do area 1/2 8 times 19 or 19 times 8, whichever way you want to do it. And that ends up being 76.
Awesome. So just applying these different formulas. We've got several different formulas for several different equations.
All right. Now, looking at this particular figure, it just says area of the figure. Is this any special type of figure?
Well, I can almost see that it looks like, we've got some kind of quadrilateral with an extra piece hanging, like a triangle hanging off to the side.
So, I mean, if you look at it, this is actually what kind of shape?
It's really a pentagon.
And we don't know a formula for area of a pentagon. So this is one where we might have to use that postulate in dealing with area addition, which basically means maybe find parts of it. Okay? So, how are we going to do this?
Well, I'm looking at some properties that we know.
Okay.
Okay. And I'm looking at the diagonals that I'm given.
Okay.
And I see within just the quadrilateral part of it, so I'm ignoring that extra triangle up top.
Okay. When technically you could say, well, this is actually a quadrilateral too.
Right. I know.
So
I'm going to get there in a second.
Yeah, I know. I'm just wanting to make sure we know which quadrilateral you're talking about.
Okay, yes. Sorry.
Which quadrilateral you're talking about.
I'm talking about the one that looks kind of like a parallelogram, possibly.
Okay.
All right.
This is the one we're talking about.
Yes, that's the one I'm talking about. And I'm going to talk about the other one in just a second, too. So as I'm looking at this one, I noticed that I've got 2 diagonals drawn in. And the diagonals are bisecting each other, so it is a parallelogram.
Perfect.
And they're perpendicular to each other.
Which means?
So it's a rhombus.
So this technically is a rhombus. Perfect.
And I know that it's not a square because the diagonals are not congruent.
Perfect.
Okay. So I'm thinking for that one, because I've got diagonals, I could do 1/2 D1, D2.
And do we have enough information? Do we have the diagonals, like the actual lengths?
We really do when we add them, yeah.
Yeah. So what's one of the diagonals?
So one of the diagonals is 6, and the other diagonal is 8. So 6 times 8 is 48. Half of that would be 24.
Okay, now that's not my final answer,
That's
right?
only the area of just the piece that you have in
That's
blue.
really this right here. That's the 24, if you want to think of it that way.
Right.
Okay.
Okay, now, the other quadrilateral that you were looking up at the corner looks like it's a rectangle because we have 4 right angles. Now, I'm only doing half of that because I don't want to overlap a part.
Good.
So I'm really just looking at the right triangle that's in that top corner. That's what I want to find the area of, and I need to add that to the 24.
Good. And I like that she said, you don't want the whole thing because that would be overlapping. So you only want this extra piece, which is that rectangle. Right now, if this whole quadrilateral is a rectangle, that means, what do we know about this
So
side?
opposite sides are congruent.
So that
so
means
that's
this
also
is
a 3.
and that's a 4.
So then I could find the area of that rectangle. And I've got my base and my height, so area is going to equal 1/2 of 3 times 4. So half of 12 is going to give me 6. So I can add that 6 to the 24 and get a total area of 30. So this is using that area addition postulate that we looked at before.
And there's a variety of ways. Like I could think about, you could find the area of, basically, if you think about it, all of those,
You have 5 little congruent triangles.
all of those triangles are congruent. So you could find the area of one of those triangles, which
Times
is
that.
6, and multiply that by 5 and get 30 as well.
Absolutely.
So it just depends on what you see.
Okay. For this last one, what shapes are you seeing on this one?
Okay, so kind of like the last one, I'm not seeing one, convenient shape as a whole because it's the whole figure. So I see, it looks like at the top, it looks like it is a trapezoid.
Okay.
And on the bottom is a rectangle.
Wonderful. And so that's kind of our plan, is we want to then find the area of the trapezoid and the area of the rectangle. Okay. Now, let's think about formulas, make sure we're good with those.
All right, area of a trapezoid is your base 1 plus base 2, that quantity times the height all over 2, and then the rectangle is just base times height.
Okay. So, which do you want to start with?
I'm going to do the rectangle first because
Okay.
usually that's a little easier.
And they even give you 2 of the sides of your rectangle, so we know
exactly.
we're set. All right.
So area of the rectangle is going to be 8 times 16, which is 128. So that's that area. And notice the rectangle and the trapezoid don't overlap. So we can find each and add them together easily.
You got it.
All right.
Okay, so what do you know about the trapezoid? Do you have everything you need there?
Well, I see a height. I see one of the bases. The other base is not labeled, however, it's also the side of the rectangle, and we know opposite sides are congruent, so that's 16. So yeah, I do.
Okay.
All right.
So then let's put them in.
Okay, so we're gonna do for the trapezoid. So the base 1 plus base 2 would be 16 plus or 10 plus 16, whichever way you want to do it. That quantity times 3 all over 2.
All right.
So when you go ahead and simplify that down, it ends up being 39.
Okay, so we've got a 39 for our area of our trapezoid. We had 128 for our area of our rectangle. So what do you know about the area of the figure?
The total area is 167.
Okay. So again, notice that we're just finding the area of each and putting them together. We didn't have any overlapping parts we had to worry about on this one.